Okay, in this analysis we're going to do a 2D heat transfer problem. So when you bring up console, you should get an option here. If you left click on 2D, we're going to step through this by clicking next. You may see a few recently used depending on what you've done previously. If not, left click on heat transfer, left click on heat transfer in solids, then come to the next step, which defines the type of problem, transient or stationary, and let's set this up to do a time dependent problem. So now we're going to click finish, and you should see something that looks similar to this. Here's our grid space we're going to put our geometry on. So we're going to do a problem very similar to the mechanics problem, also given in a separate video, where we have a circular hole in the center of a large plate, and we're going to look at heat flow in the vertical direction. So let's first create a geometry. So if you need to, left click on geometry, and let's create a rectangle, left clicking here. You can put this anywhere. I'm going to make a square of unit or close to value of 1. It doesn't have to be exact. If we come back over here and click on this left arrow, it'll expand this down and you'll go to rectangle. Let's change this width to 1, and let's change the base to 0, and then click build all, and it'll make a slight adjustment, so it's these parameters. Okay, now go back, left click on geometry, and let's zoom out a little bit, and now let's put a circle. Left click on circle, left click there, drag, and click again, and now come over to circle, and let's make this a radius 0.1. Everything else is hold, so it should be a base at the corner point. Alright, go back, left click on geometry, and now we're going to subtract the circle. So remember, we want a hole in the center. I'm using, also important to note, I'm using quarter symmetry. So it turns out with these boundary conditions and the symmetry of the hole, we can use quarter symmetry to solve this problem. So now we're going to click difference, and you'll get this. Alright, so now you can do zoom extents to bring this into view, and that's our geometry. So now you can bring this back together. Let's go to materials, and let's right click and open material browser. Here I'm just going to select a material that's given within COMSOL, acrylic plastic, and I'm going to right click and add material to model. Right? So now you notice this is contained within our model, so this is our geometric domain 1. Also notice when you get down to the bottom, we're missing thermal conductivity. So let's just put in a value. I'm going to use 10. I'm going to use 1 for specific heat, and now everything's checked off. We're good for thermal problems. Alright, so that defines material. If you left click on heat transfer and expand this, this first icon gives you a number of things. One important one is it'll show you the equation. So here is our time dependent term. So T is our independent variable temperature. Here's your Laplacian gradient on temperature. K is conductivity. We're pulling conductivity, density, heat capacity from the acrylic material. So that's good. Other thing to note is COMSOL often starts out as default natural boundary conditions 0 everywhere. So it's say thermal insulation. We're going to override this in a moment, but first on initial conditions, so since this is transient, we need to define temperature everywhere. We're going to leave it at room temperature. Now let's come back here and right click. So if you right click here, just go down, click, left click on temperature, and on the top let's put this at 350 Kelvin. So when you left click, you need to add, so that adds that boundary. And now let's add another temperature boundary by right clicking again here, left click temperature, left click on this boundary and add it, and now we're going to specify that. Let's leave it at room temperature. Turns out you'll get the same solution if you put a thermal gradient across the end, if you did half symmetry, top and bottom. So we can just put constant temperature across here. You'll see that you get the same type flux. Alright, now let's go back to our other boundaries. We're going to define a heat flux. So instead of using insulation, we're going to explicitly say that these two are insulated by some material on the interfaces. In addition to that, this problem is symmetric due to the temperature drop across the top and bottom. So as flow goes around this way, it's symmetric on this boundary. So our heat flux is 0 on those three. So since we've clicked those three, you have to make sure you add them. And now we're done. So if you actually go back and look here, you'll see these are all overwritten. Alright. Last step in setting up this problem is we have to mesh it. So I'm going to start out with the default mesh, which is given here. And now we're done. We've set up everything we need to go and solve this problem.